It is a beautiful and grateful day. Let's embrace it.
Yes, it is, partner. Today, people, we are about to discuss Chapter 5 from Violins to Videos of Ian Stewart, Nature's Number.
This chapter begins with a narrative of how applied mathematics and pure mathematics come together to create something more powerful and captivating than each of them could have created alone. And it began at the start of the 16th century with the problem of the vibrating violin string.
Furthermore, action rational mathematics is utilized in the study of phenomena such as radiation, magnetism, electricity, and other forces, with researchers using mathematical teaching, hormones, and theories to explain how these processes function in our universe. To build on the concept, consider how values were used to investigate vibrations and the contributions of various participants in the debate.
The way the violin string vibrates, according to the Greeks, is determined by how it is plucked. It was eventually discovered that the frequency of vibration determines the pitch of the violin's tone.
Greeks discovered vital proof for the theory that a string may vibrate at many different frequencies. While studying violins in the 16th century, they showed that the pitch depended on the position of the notes places along the length of the screen. With the more nodes, the higher the frequency.
That's true, partner. Each frequency has correspond to a different configuration of the moving string, which can take on a variety of shapes. The Greeks demonstrated this concept by demonstrating how the pitch of the violin is affected by the notes. Furthermore, Angela, did you know that the equivalent vibration here are referred to as standing vibrations? Specifically, waves that move up and down but not travel along the string, which is also known as amplitude of the waves, and it determines the tone's loudness. The waves are sinusoidally formed as a sine curve, a trigonometrically generated recurring wavy line of fairly attractive pattern.
Now, partner, do you know who is Brooke Taylor is?
I have no idea who he is. All I know is the place Brooklyn.
Well, partner, let me educate you. Brooke Taylor is an English mathematician that published the fundamental vibrational frequency of a violin string in terms of its length, tension, and density. And after Taylor's theory, three mathematicians, Jean Leron D'Alembert, Leonhard Euler, and Daniel Bernoulli are commented over the equation of vibrating string. Jean Leron D'Alembert, he showed that many vibrations of violin string are not sinusoidal. Standing waves in response to the Alembert's work, Swiss mathematician Leonhard Euler worked out the wave equation for a string and solved it. In fact, it is a particular differential equation, meaning that it involves not only rates of change relative to tone, but also rates of change relative to space almost immediately. Euler got into an argument with Daniel Bernoulli. He also solved the wave equation Euler, but a totally different method according to Bernoulli. The most general solution can be presented as a superposition of infinitely many sinusoidal standing waves. This argument ended when it was declared that both the Euler and Bernoulli was right. They both depend on the shape that can be emphasized as a superposition of an infinite number of sine curves. A part of the curve that matters is the part between the two endpoints. Moreover, when the controversy about the vibrating string was resolved, mathematicians hunt for a bigger game. With this, they found out that violin string is a curved one-dimensional object, but the object with more dimension can also vibrate.
And, partner, the drum is the most obvious musical instrument that uses two-dimensional vibration because a drum skin is a surface rather than a straight line. Mathematicians have turned their attention to drums, beginning with Euler in 1759, who obtained another wave equation. The intriguing distinction between the borders of a violin string and the boundaries of drums led to the conclusion that the true role of the boundary appears in two or more dimensions. For a drum with a, for a drum with a closed curve or circle boundary that restricts the possible motion of the drum skin. The wave equation for the motion of various shapes of drums was solved by mathematicians in the 18th century. But the wave equation began to move out of the musical domain and establish itself as an absolute important aspect of mathematical physics.
During the 18th century, significant figures included William Gilbert, a physician to Queen Elizabeth, who was the first to characterize the Earth as a massive magnet. He began the narrative of electricity and magnetism by observing that electrically charged materials may attract or repel each other.
Second is Benjamin Franklin, who proved in 1752 that lightning is a form of electricity by flying a kite in a thunderstorm. Third is Luigi Galvani, who noticed that electrical sparks cause a dead frog's leg muscle to contract. And last, Alessandro Volta, who invented the first battery. Throughout much of this early development, electricity and magnetism were seen to quite distinct natural phenomena.
Following their rival, Michael Faraday demonstrated that magnetism and electricity were two different facets of the same entity, electromagnetism. He worked for 10 years to prove that electric current could cause magnetic force, and he succeeded in 1831 when King William IV inquired about the usage of his scientific parlor tricks. Faraday respectfully replied that he would tax them one day. After they came Michael Faraday, he was shown that magnetism and electricity were two different aspects of the same thing, electromagnetism. He spent 10 years to prove that electricity current could create magnetic force in 1831, and he succeeded. He was asked by King William IV about the use of his scientific parlor tricks, and Faraday politely replied that one day he will tax them. That electricity motor and the electrical generator were among the first practical applications. Faraday also improved electromagnetism theory, casting his thoughts in physical images, the most fundamental of which was the concept of the line force.
I know that you all know that if you place a magnet under a sheet of paper and sprinkler iron fillings on top, they will line up along well-defined curves. Faraday's interpretation of these curves was that the magnetic force did not act at a distance without any intervening medium. Instead, it propagated through space along curved lines, and same went for electrical force.
Now, we'll talk about another prominent person named James Clerk Maxwell and his formulas. He expressed Faraday's idea about lines of force in terms of mathematical equation by 1864. He had refined his theory down to a system of four differential equations.
First is Gauss' law, for electric fields where the integral of the electric field over the arc of the surface, which is equal to the enclosed charge divided by the permitting of free space. Second is the correspond formula for magnetic fields. The integral of the magnetic field over the area of the surface equals to 0. Third is Faraday's law of magnetic induction, where the integral of the electric field over the infinitesimal of closed loop is equal to a negative charge in magnetic flux divided by change in time. And fourth is Ampere's law plus Maxwell's displacement current. The integral of magnetic field over the infinitesimal element of closed loop, which is equals to permeability of free space multiplied the current plus displacement current.
From there, a series of simple algebraic manipulations extracted the wave equation from Maxwell's equations, which imply the existence of electromagnetic waves travel with the speed of light, and life itself is an electromagnetic wave, and violin string can vibrate at many frequencies. So according to the wave equations, so can the electromagnetic violin string can vibrate at many different frequencies, producing different sounds as visible electromagnetic waves, with different frequencies produce different colors.
Let me discuss the applications of equations in physical world. We have Heinrich Hertz, who was a German physicist during 1886, generated electromagnetic waves at the frequency that we now call radio and detected them experimentally. And second is Guglielmo Marconi, who on 1895 successfully carried out the first wireless telegraphy and transmitted and received the first transatlantic radio signals in 1901.